Now, we will consider a special case of motion of charged particle in a magnetic field, which is when the charged particle is moving in a plane and there is a uniform magnetic field that is perpendicular to that plane. In this case, we have a special type of motion under of that charged particle under the action of the magnetic field. So, for example, assume that I have a charged particle moving in the plane of the screen here, okay? And I have a magnetic field. Assume that it is normal to this screen and into it. So the magnetic field now is perpendicular by default to the velocity of that particle, okay? Because the particle is moving in a plane to which the magnetic field is perpendicular. So this is depicted here. So here we have these crosses, and as you can see, they are equally spaced, and they tell us that we have a magnetic field into the page, okay? So the magnetic field here is into the page. And we have this particle moving here. Now, in this case, the particle has no component of its velocity along the magnetic field, because the magnetic field is perpendicular to the direction to the velocity, okay? So the velocity has no component along the direction of the magnetic field. In this case, what will happen is that the particle will move. I'm talking about a uniform magnetic field. The particle will move in a circular orbit, and we will see what are the characteristics of this orbital motion of the particle. So it will move actually in this circular orbit, and it will move with constant speed. So this is uniform circular motion. So the particle in this case will perform uniform circular motion. To understand why it will move in a circle, first of all, consider, for example, if it is here, then this is V, okay, B is inside, so F by the right-hand rule is upwards. Now, what will happen is that the particle's motion will be deflected. Once it's deflected, it will be deflected a bit because it already has a speed. So if it's deflected in this direction, then again a force also towards the center now will be acting. It will be deflected again. Another force towards the center will be acted, because always the force is perpendicular to V and B, okay? And therefore, the force always will be towards the center. And you can check that in this case, this applies to wherever your particle. So the particle will end up moving in a circle. You can check this by trying to draw, for example, what happens if it starts here. Try to show that if it happens, if the particle is deflected and it's here now, try to convince yourself that the force in this case will be towards the center again, and so on. So it will end up moving in a circular orbit and moving with constant speed. Of course, the question here is, why is the speed constant in this case? Well, simply because the force is normal to the velocity all the time, okay? The force is normal to the velocity all the time, because this is from the definition of the velocity here. The vector F is normal to both V and B. Okay, I mean, this is something general. When you have the cross product, when you have the vector product, A cross B, the result of A cross B is a vector that is normal to the plane containing A and B, which means normal to both A and B. Okay, so generally, the force vector is always normal to the velocity of the charged particle. And the meaning of this, when it is normal, is that it is normal to the displacement, because the displacement is always along the velocity. A force that is normal to the displacement does no work. And if that force does no work, it doesn't transfer kinetic energy to the particle. And so the speed of the particle, because the kinetic energy depends, is just the square of the speed, proportional to the square of the speed. The speed of the particle remains constant, okay? And therefore, magnetic forces, this is a general rule, a magnetic force, when it acts on a particle, charged particle with given velocity, then it does not transfer energy to that particle. So magnetic field does not transfer energy to that particle, in contrast to the electric field. So this is something quite general. And so what does it do? So because it doesn't change the speed, but it changes the velocity. So it accelerates it. And as we know, a particle moving with constant speed but with a variable velocity is an accelerating particle because the direction of the velocity vector is changing, and therefore that's the definition of the acceleration. And so we have a particle moving now in a uniform circular motion, and we can apply now what we have learned before about the uniform circular motion to find the relation between the radius, for example, and the velocity and the magnetic field. So we say take the particle at any point and say that the net force in this direction towards the center is just the magnetic force, and this is equal to ma according to Newton's law. Okay, what is the magnetic force? It's qvb. What is a according to for a particle moving in uniform circular motion? It is v square over r. So qvb is equal mv square over r. So this is the Newton's law expressed for the particle here moving in this magnetic field, the charged particle moving in this magnetic field. From this equation, you can find many quantities. An interesting quantity is the radius of the orbit. So if you isolate r, you get r is equal mv over qb. Okay, so r here depends on the velocity, the speed, and also on q and b. Now, another quantity is the angular speed of the particle. You remember omega, the angular speed, which is the speed divided by the radius in this case. Okay, and this is qb over m. Note that it's independent of the speed. Okay, so this is the angular speed. What is how many radians per second does this particle move? So this is independent of the speed of the particle. It depends just on this combination. Another quantity is the period, because the particle is moving in a circle in the period, the time that takes the particle to make one complete revolution. So this is the distance for one complete revolution divided by the speed, and this is what you get, which is just the same at 2 pi over omega, and this is what it is. Again, it's independent of the speed. Now, the frequency, 1 over t, is just the inverse of this. So it's qb over 2 pi m. So this is, these are the quantities that we can derive for a particle moving in a plane in a uniform electric field and thus moves in a circle. There is a couple of checkpoints that worth trying before you proceed. Now, what happens if the particle's velocity is not in the plane perpendicular to the field? In other words, this field is still in this direction. The field is in this direction into the plane, but the particle is not moving in the plane of the board, but rather it enters the field at an angle. So it has two components, one component perpendicular to the field and the other component parallel to the field. In this case, the particle's path will be helical. Okay? The particle will move in a helix in this case, because it will move in a circle, but now because of the speed or the velocity in this direction, which is not affected by the field, okay, because this is parallel to the field, that velocity, this component velocity, is not touched by the field, so it remains. Okay, so it deflects it, but it starts taking this path, which is a helix. Now, all the equations that we have derived actually for the orbit, the circular orbit, still valid. I mean, this is the radius of the orbit, this is the angular velocity, and so on, and this is the period, except that now you have to have v, you are using here, going to v perpendicular, which is the component of the velocity, the magnitude of the component of the velocity that is perpendicular to the field. So, for example, here, if the particle has in 3D, it has its perpendicular component is in the component perpendicular to the field is in the YZ plane. Okay, so its magnitude is Vy. It has ZY component and Z component. So its magnitude is Vy square plus Vz square. The X component here doesn't enter into the V that appears here when you use these equations. So let's consider a simple application of these relations. So we have a proton moving in a circular orbit of radius 14 centimeters and in a uniform magnetic field equal to 0.35 Teslas perpendicular to the velocity of the proton. So the proton will follow a circular orbit in this case. What is the speed of the proton? Well, the simple relation, V is equal QBR over M. I substitute everything and I get what is the speed in this case, which is 4.7 times 10 to the power 6 meters per second in this case. Now, interesting question, I leave it for you to answer. What if the electron rather than a proton moves in the direction perpendicular to the same magnetic field with the same speed? So we have got the speed, it's the same field, but it's electron, not a proton. So it's the same charge but negative. What about the mass? So will the radius of its orbit be different? So check out the relations that we have derived for the orbit and see what would be your answer in this case. Now, usually, in reality, in many cases, we have particles moving not only in a magnetic field or an electric field. Actually, we have charged particles moving in both electric and magnetic fields. So if a particle moving in a region where there is an electric field and there's also a magnetic field, okay, then in this case, that particle will be experiencing a force, electrostatic force or electric force due to the electric field, and the magnetic force due to the magnetic field. Okay? So the total force that the particle experiences in this case will be the net force, the vector sum of these two forces. Now, this force is called the Lorentz force, and it is given by this expression. So the net force in this case, on a particle moving in a field, electric field E and magnetic field B, will be Q times E. This is the field, electric field, the field electric force, and QV cross B, which is the magnetic force. So this total force is the vector sum of these two forces. Note that, of course, here the F, for example, for the electric field, it's either parallel or anti-parallel to the electric force is parallel or anti-parallel to the electric field, depending upon Q, the sign of Q. But the magnetic force in this case is perpendicular to the magnetic field. Of course, the simplest example where a particle is moving in a combined electric and magnetic field is when the charged particles forming our tissues, when they are in microwave radiation, for example, your phone cells. You know, the signals, electromagnetic waves that we use to communicate signals in using our phone cells, for example, they are electromagnetic radiation. What's electromagnetic radiation? It is actually combined electric and magnetic field propagating in space. So at every second now, the charges in your body are feeling both in both an electric and a magnetic field. Of course, these are very small, so we believe that they are harmless or less harm. But this is a situation where you are in both electric and magnetic field at the same time. Now, an interesting application of particles in both electric and magnetic field is what we call the velocity selector. In this example, assume that we have a source of particles and of charged particles, positive particles, and they are sent into this region here. Now, they are coming with different velocities, but for some applications, okay, they have different speeds, different velocities. They are moving in the same direction, so they have different speeds. I want to select only the particles that have a given speed and eliminate the others. How you can do that with usually, you know, microscopic charged particles, like a beam of electrons or a beam of protons, for example. How you can do that? Well, the way to do that is what we call velocity selector in this case. And the idea is to let these particles pass in a crossed electromagnetic field. So the electric field is generated by two large plates. So you have a uniform electric field from left to right, as you can see here. These are the yellow lines are the electric field lines. And the magnetic field is applied, for example, by a solenoid or was that, and it is into the page. So these are crossed, they are perpendicular to each other, okay? So the particles enter here. So a particle entering here will feel both a magnetic electric force and a magnetic force. The electric force will be to the right because the particle is positively charged, so it's to the right, okay? The magnetic force, according to the right hand rule, it is to the left. Why? this is V, close towards B, which is into the page, it is to the right, okay? So we will have Fe, electric force, and Fb, the magnetic force, acting in opposite direction. So what we do is we say, okay, we now note that electric force depends only on the charge, but the magnetic force depends also on the speed, because its magnetic force is QVB. Okay, so it depends on the speed. Now, if we tune for a given particles, for a given for a given electric field and a given magnetic field, this is the total force acting on that particle. This is the expression. As a magnitude, of course, because the force, the magnetic force in this case, the angle between V and B is pi over 2, then the magnitudes in this case will be just QVB. Okay, there is no angle other than the angle between V and B is just pi over 2, so we don't have sine theta. Now, if we tune things so that some of the particles that here do not get deflected, so it's their velocity so that they do not get deflected. In this case, the magnetic force is equal and opposite to the electric force, and their magnitudes therefore are the same. So you equate them. So here this is a function of V. Okay. So in this case, if you isolate V, you get V is equal to E over B. Therefore, if you want, for example, particles having this velocity to be selected, that's you want them to move here without being deflected and the others being deflected, then in this case you tune these, tune E and B so that their ratio is equal to that velocity, and then in this case you guarantee that the particles coming with this velocity will move without deflected. Other particles will deflect either to the right or to the left, okay, depending which one is larger, the magnetic force or the electric force. So this is velocity selector, an application of the Lorentz force. It's a simple application of Lorentz force. There are other applications also.